Welcome, Madam Professor Chandralekha Singh.
Thank you. I'm happy to be here.
Yeah, great to see you. Yeah, great to see you.
So, welcome, madam.
Good evening, everybody. I extend a warm and sincere welcome to the esteemed President of IAPT, Professor P.K. Ahluwalia, our Senior and Honorable Professor, Professor H.C. Pradhan, the Secretary of IAPT, Ma'am Rekha Ghorpade, our distinguished speaker for today, Professor Chandralekha Singh, and all the respected members of that we come together for the second lecture of the lecture series on physics education research. IAPT has taken the initiative to organize the lecture series on physics education research, which is a commendable endeavor aimed at advancing the field of physics education in India. We are honored to have experts of the field as our distinguished speakers for the series. We will be privileged to hear from them as they share their knowledge, experiences, innovative and transformative ideas. They will shed light on cutting-edge research findings, emerging trends, and best practices in physics education. From conceptual understanding to problem-solving skills, from fostering scientific inquiry to utilizing technology. Second lecture of the series, I am delighted to extend a very warm welcome to our esteemed speaker, Professor Chandralekha Singh, Professor of Physics and Astronomy, Pittsburgh University. She is also the founding director of the Discipline-Based Science Education Research Center. Ma'am, we are honored to have you with us today. I would like to invite Professor H.C. Pradhan, former director of Homi Bhabha Center for Science Education at BCSC TIFR, and also former president of IAPT, to kindly chair the session. Professor H.C. Pradhan is a renowned physicist and expert of physics education research. He has lots of interest in the study of students' alternative conceptions in physics and was instrumental in designing and implementing numerous training programs in science education. Sir, with your permission, we would like to start the session.
Thank you, Sapna Madam. Colleagues, I'm really thrilled to chair this session. And as I was going through today's speakers, Chandralekha Madam's CV, I was so impressed. And I'm so happy that you have accepted our invitation. And I think you are a person who really travels, both areas of physics. The research in pure physics in a field like condensed matter, which is not easy at all. In fact, I have been introduced to many body theory, and I know how difficult it is to unravel the mysteries of many body physics, and in particular condensed matter. It's very exciting. It's exciting because things which are there, they're very much closely related to everyday life, and still the mysteries, they really intrigue you. And in such a field, Madam has worked for many years, and at the same time, I'm so happy to know that she has really been interested in physics education, in physics teaching, and done very, very important work in physics education. Madam, we are really eager to know what you think of physics education research in the world currently. We're trying in India, and I think we look forward to your guidance and your continued contacts, so that, and I think, especially in India, with the new education policy, it looks to me that there will be a lot of scope for many, many collaborations across colleges, across universities, and so on. And I think IAPT will have to play a very, very important role in all this. And at this juncture, when physics education research in general, and science, in fact, physics education research in particular, and science education research in general is going to be more and more important. I think IAPT is embarking on a very, very important program. Professor Ahluwalia mentioned to us what we are actually planning for the whole year. And I really wish, the whole program of IAPT for this year a grand success. And I think the success really depends on all of us. And I'm sure with the guidance of Professor Chandralekha Singh and the community of men and women physicists all over the world, we shall be able to work out a collaboration that will enable us to change the face of physics education in the country. It's high time that we do that. And I think the new education policy will definitely help us in that process. So I'm eager to know now from Professor Chandralekha Singh her actual talk. And with this, my introduction, I shall request Dr. Sharma to take the reins in hand and begin with the proceedings of the lecture. Thank you all.
Thank you, sir. Thank you very much. I would like to request Professor Ahluwalia to kindly give his message and welcome Ma'am Chandralekha Singh. Sir, kindly unmute yourself. Ahluwalia, sir.
So a very good evening and respected Professor Pradhan, our distinguished speaker of the evening, Professor Chandralekha Singh, our General Secretary, Professor Rekha Ghorpade, distinguished members from IAPT and the participants of this seminar. Formally, I would like to welcome Professor Chandralekha Singh and Professor Pradhan and all other participants to this particular program. In fact, dear colleagues, I have been really looking forward to meet Chandralekha Singh. The reason is that we have been following her work, which is such a big body of work in the last almost 20 years. And I was reading how she actually made a transition from condensed matter physics to physics education research. I enjoyed, Chandralekha, that small write-up on your webpage. I really enjoyed reading it. I think that is very inspirational. And I and Sapna both have drawn a lot of inspiration from your work also when we have been doing this kind of work in our small ways also. So thank you very much. And we would love to hear from you something exciting and hope this will also strengthen our association, IAPT, and with India. I think your roots are very much in India, so you would love to be with us and guide us in making PER a very, very challenging program in the universities and institutes. Thank you for accepting our invitation. And once again, I welcome you. Thank you.
Thank you so much. I'm really, really delighted to be here. Could you please enable sharing of the screen so that I can actually share my slides? Because right now it says host has disabled participant screen sharing.
Yeah, we will. Sapna, please provide her the right to share her screen.
Yeah, that I'll do. But before that, I will ask Ma'am Rekha Ghorpade to give a brief introduction of our speaker. Ma'am Rekha Ghorpade.
Yeah, thank you, Dr. Sapna. Respected Professor H.C. Pradhan, who is my teacher, guide and mentor. Professor P.K. Ahluwalia, President IAPT. I can see Professor Ajay Ghatok has also joined. So we are really delighted and we are privileged to have him here with us. All other respected colleagues who have joined online for this session. I am extremely happy to have this second lecture in the series of PER. And I wish to thank in the beginning itself to Dr. Sapna Sharma for shouldering this responsibility. So I'm given a very, sorry.
Please continue, ma'am.
Yeah. Actually, some problem is there in my connection. Yeah, I'll just, in a few seconds, I'll get connected. Yeah, are you able to hear me, sir?
Yes, yes, ma'am.
Yeah. There is some problem with. Okay, I'm back. Yeah, so it's a very pleasant task, and please excuse me for that short break here. I'm working from a very remote area where the connectivity is a problem. We are really delighted to have Professor Chandralekha Singh with us today, who is a distinguished speaker for this lecture series, the second of the lecture series. Professor Chandralekha Singh is a distinguished professor in the Department of Physics and Astronomy and the founding director of Discipline-Based Science Education Research Center at the University of Pittsburgh. She is a past president of American Association of Physics Teachers. She has been conducting research in physics education for more than 2 decades. She is a fellow of American Physical Society, American Association of the Advancement of Science, and American Association of Physics Teachers. And we also would give you the links, where more information also will be available. Now she will discuss, using her research in physics education, how research can be used as a guide to develop curricula and pedagogies to reduce student difficulties and for making physics equitable and inclusive. So we are really happy to have Madam Chandralekha Singh with us. And without taking much of my time, I would like to call upon Dr. Chandralekha Singh for her wonderful lecture. And I'm sure all the participants are going to have a really very good time with Madam Chandralekha. Over to you. Sapna, if you.
Ma'am, I'm just trying.
But I think with our this kind of license, Madam Chandralekha can share her screen. Are you finding, Madam, some difficulty in sharing the screen?
I am not able to share screen. I mean, like,
okay. So Sapna, what you do is just make her the host.
1 minute, ma'am. I am just trying it.
You can make her co-host as well.
Yeah, you can make me co-host. That would work. I'm so delighted to be here. I'm going to actually share some of the research studies that I have done. And, hopefully we can build some collaborations as well along the way. So I'm just waiting for Sapna to allow me to share screen. So
sorry, ma'am, I'm finding it really difficult because I'm trying. I'm just trying. Sorry for the delay. Actually, I'm just
Sapna.
Yeah.
Just on the participants list, in front of Madam, there will be 3 dots.
Okay.
And there you just click and see there is the option of make host.
Yeah.
So just click that.
Yes. Okay.
Right.
Okay. Yeah. I have
done now I can share my screen.
Yes.
Right,
now,
right.
Madam.
Thank you. Thank you, ma'am. Thank you, Rekha, ma'am.
Thank you. Thank you very much.
Okay, so I hope you can actually share my, see my screen, right? Yes. All right, so, I am really, truly delighted to be here. And I hope that some of the research studies that I'm going to talk about will actually spur some collaborations and, further work. So the first research study that I was going to talk about is related to what does it mean to think like a physicist? What is the role of intuition in physics problem solving? And notice that, it's really difficult to figure out what it means to think like a physicist, because if you give the same problem to physics faculty and students, oftentimes those problems are so easy for faculty because they have thought about it a lot that they're not really problems, because problems have to be novel activities, but they turn out to be exercises, right? So we don't want to give those kinds of problems when we want to think about how faculty would think on their feet when they are given a novel problem that they haven't thought about before. But you can find some problems like that. And so we found a problem, for example, some problems, and here is one problem that I'm going to tell you about, which is a non-intuitive problem that was given to 20 physics faculty and many students in introductory physics courses. And we also, for faculty, it was given in a one-on-one interview situation where they read the questions and tried to think about those questions on their feet. And notice that, this is the situation in which we put our students, right? I mean, when we actually discuss a particular problem, then later when we are giving them quizzes or exams, we don't give them exactly the same problems. We give them something slightly different, and we want them to be able to actually transfer their learning to those new situations. So, students always have to think on their feet. Like, for example, we might talk about the ballerina problem, she putting her arms close to herself and putting her out, and why she spins faster or slower in those situations. And then maybe like, in the exam, the question might be about a neutron star that is collapsing and slowly rotating. And then we ask them, what happens when the radius goes from a certain value to a certain value, right? And these problems, like the ballerina problem and the neutron star problem, they're both, angular momentum conservation problems. So they have the same deep features, but the surface features could be very different. And students can really get distracted by those kinds of things. And so they might think of the neutron star problem as a totally novel problem that they may struggle with, whereas for faculty it may not be difficult. But the problem that we picked, were problems in which professors usually have difficulty because of the fact that they hadn't actually thought about these problems, and they don't usually assign these kinds of problems to their students. So what is this problem? So this is a problem in which you have a spinning wheel that spins and falls on the ground and then slips for some time, and then finally starts to roll without slipping, so that the V final becomes equal to R times omega final. And the question is asking, how does the friction on the surface, how does the kinetic friction on the surface determine this final speed, V final, at which the wheel will start to roll without slipping? And you can see that this is a problem. Can you please mute yourself? If this is a problem in which you don't really have, faculty haven't thought about it. Dr. Reshma, could you please mute yourself? So this is a problem about which faculty do not have a lot of intuition. So they have actually been put in a situation in which students usually are, because there are two things that are critical. One is how much is the coefficient of friction, and the other one is how long does it take to start rolling without slipping. So, Dr. Reshma, can you mute yourself, please? So the thing is, so the final speed actually does not depend upon the coefficient of friction. So and the reason it doesn't, you can use angular momentum conservation about the point where the wheel first touches the ground. And since the angular momentum is conserved about that point, the frictional coefficient cannot determine the final speed at which the wheel starts to roll without slipping. Another way to do it is to use linear kinematics and angular kinematics equations, and then set V final is equal to R times omega final, and you'll see that the frictional coefficient drops out. But we found that faculty really did have a lot of difficulty solving this problem, and oftentimes, initially at least, they thought about only one of those things, like how much is the coefficient of friction or how long it takes to start to roll. But the point is, what we found is that faculty still used something that we would call thinking like a physicist. They thought about limiting cases. What happens when there's no friction? What happens there's infinite amount of friction? It may not help in this situation, but it still is a good heuristic, I mean, if there is a lot of, the frictional coefficient is very large, the wheel would start to roll without slipping quickly, and there'll be the total amount of energy that is dissipated in the form of heat and other things will be the same regardless of the coefficient of friction. They also thought about, analogies with familiar situations, something that we should be really helping our students learn. For example, when a wheel is actually, when an airplane is landing, how would the friction on the surface determine the final speed at which it starts to roll? They also thought about, principles of physics that could be relevant here, what different conservation laws, linear momentum, angular momentum, conservation of energy, etc. So notice conservation of angular momentum is tricky because you have to think about the point about which the angular momentum is conserved. But anyway, the point was that you could really tell that faculty knew how to solve problems, and if you gave them enough time, they would be able to solve these, whereas the students were all over the place. So really what we learned is that, faculty, even in this novel problem, were thinking systematically. Many of them went to the board and they drew a diagram. They thought about, what are the things that are given, how do you act, what are they finding, thought about, going through systematically the kinds of effective problem solving strategies that we should really be helping our students learn. We also had given to faculty and students, a ballistic pendulum problem. This was the problem, which was about like two putties that are actually hanging from a ceiling. One of them raised to a certain height. It falls when it's let go. It goes and collides with the other one. The two things stick, and then the two things go up together. The question was, how would you find the final height to which the two things go up together in terms of initial height? By the way, this was given both in open-ended format and also in multiple choice format to students, 2,000 students from 14 different universities in the US. And what we found is that only 27% of the students after instruction provided correct response that you should be using both mechanical energy conservation and linear momentum conservation to answer this question. Because when the wheel is coming, when this putty is coming down, you should be using conservation of mechanical energy to figure out what will be its speed when it hits this ball B. That when the two things collide, this is completely an elastic collision. You have to use linear momentum conservation. And then when the things are going up, conservation of mechanical energy. You can see that many students are thinking that, you should be using only one or the other, and not both. So this is a very difficult problem for students. In fact, we did not find that students actually got very similar scores on the spinning wheel problem and on this putty problem, two putties having ballistic pendulum problem. But faculty thought that this problem would be a lot easier for their students than the other one. Some of them even said, oh, I have just done this problem in class, so I know that this is a really easy problem, whereas that spinning wheel problem would be really hard for my students. It turned out that was not the case. Students had equal difficulty with both of these problems. And if you're really thinking about the fact that, faculty think that this would be easier, this is because they're not thinking about the difficulty of the problem from their students' perspective. They're not putting themselves on their students' shoes. They're thinking about the difficulty of the problem from their own perspective. And this is a huge mistake in teaching and learning, because we should really be thinking about the prior knowledge of the students and putting ourselves in the students' shoes to think about how to actually help them, build on that prior knowledge effectively so that, their learning is meaningful. Because there needs to be proper impedance matching between where the students are and, where you are wanting to get them to. So in order to have proper impedance matching, we should understand that this problem is not a lot easier for the students than the spinning wheel problem. And in fact, you can see that this is a problem which is a three-part problem. Something is coming down and you have to use one principle of physics. The two things are colliding, you have to use momentum conservation, and then again going up, you have to use mechanical energy conservation. And so these three things are temporally separated, and students really struggle, as you can see from student performance of 2,000 students from different universities. So what we learned from this study, we learned two things. First is that the perceived difficulty of a problem not only depends upon the inherent complexity of the problem, but also how much experience and familiarity you have. And this ballistic pendulum problem has become automatic for professors because they have thought about it a lot, but then they are not thinking that it will be a difficult problem for their students, and they are not necessarily providing the right kind of support, and they are thinking that their students would be able to do them, but you can clearly see from the performance that I showed you, they are not able to do it well even after instruction. The other thing is that, it's really important that we think about the difficulty from the student's perspective and provide them with the right kind of scaffolding and guidance. Now, I would also say that the fact that for the spinning wheel problem, faculty really thought about it in a much more systematic way, thought about limiting cases, thought about the principles of physics involved, thought about analogies with familiar situation. Those are good heuristics that we should really be teaching our students as we are helping them solve problems. Because otherwise, it's not really about, oh, we'll do the concept first and we'll do the problem solving later. The two things need to be meshed with each other so that the students actually develop a robust knowledge structure. So the conceptual understanding and building of a good knowledge structure needs to happen with effective problem solving strategies if we really want our students to learn to think like physicists. All right, so let me now go on to another research study that I wanted to share with you. And this one is, reflection on problem solving. So we all know that problem solving is a learning opportunity. But students need to reflect to learn to learn from problem solving. So in other words, if students actually did something wrong or they struggle with some problems, then they should spend the time thinking about, what did I do wrong? How would I know next time that this is what I should have done and not this? What are the deep features of the problem that make it a problem where I should be using, for example, this principle of physics and this principle of physics and not the other one that I was thinking should be applicable. So, it turns out that unfortunately, many a times problem solving is a missed learning opportunity. And if we don't actually incentivize students and support students, oftentimes, students may not use the mistakes that they make on quizzes or exams to learn from their mistakes. So the question is, can the instruction prompt them to learn from their mistakes so that they actually can become better problem solvers? And I really like this model of learning that is called cognitive apprenticeship model, which is a very broad framework for teaching and learning, which has three major aspects. One is modeling, which means that you as an instructor need to model what the criteria for good performance, how you want students to be able to solve problems, how you want them to be able to organize their knowledge of physics. But then what is also important is coaching and scaffolding. That means you want to give students opportunity to actually solve problems. And then when they struggle, you will provide them with immediate feedback and support so that they actually figure out, how to build their knowledge structure, how to solve problems effectively, how to become systematic in their approach, how to use analogies, how to actually be systematic, how to use limiting cases, etc. And last but not least, you have to fade that support. You have to have students do the things independently so that they develop self-reliance and are able to do those kinds of problems on their own. Now, oftentimes in teaching and learning, what is missing is this coaching and scaffolding. We don't provide students enough support and feedback. So if for example, if you're teaching somebody to play piano, you can model for them how to do it well. But if you actually don't tell them to actually practice in front of you and give them guidance on what mistakes they are doing or what they are having difficulty with, and just say, oh, go home and practice, that would be fading the support too soon. And you're missing out on the coaching and scaffolding part that is really important before the student actually develops self-reliance to go home and do the homework on their own. So the objective of this particular study was to actually see if we actually provide students opportunity for correcting their own mistakes for certain amount of points back, credit back. Will they actually perform later on some transfer problem which use the same principles of physics? And how much better will they do compared to some control group? Now, we did some study with Yerushalmi et al., and we actually found in introductory physics that giving students incentives to correct their mistakes before they were provided the correct solutions to their quiz problems each week really helped students solve similar kinds of problems, not exactly the same, but similar kinds of problems on the final exam. Compared to control group where the students were just provided the correct solutions after they had actually taken the quiz. Now, the same kind of study we also repeated in quantum mechanics, in undergraduate quantum mechanics to see if in this case, in advanced courses, is there any difference, in terms of like how students learn from the solutions that are provided, or is it that, again, giving them some incentive to correct their mistakes helps students perform better compared to the group that was just provided the correct solution? So I'm going to actually, so basically, I'm going to just show you this, how students did. And so when I say comparison group here, these are the students who are actually not just provided the correct solution after their midterm exams. So that the midterm exam is what is called pre here. And this is the incentivized group in which students are given incentive to correct their mistakes. And again, pre means how they did on those kinds of problems on the midterm exam. We have also divided the students into 3 groups, low, medium, and high, depending upon how they did on the midterm exam on those problems. And now this group was just given the correct solution to those things when their midterm exam was being returned. And this group actually was first asked to correct their mistakes. So they were on Friday, they were given their solutions, and something was marked there. And they knew, okay, they got 5 over 10 on this problem, but they didn't know what mistakes they had made, and they were told to open their books and notes and not talk to other people, but just open their books and notes and correct their mistake and come back and give it on Monday for a certain amount of points back. And then they were given the correct solution when they submitted their mistake. Notice that they are going through what is called productive struggle a second time. Productive struggle, actually, when you open your books and notes and figure out what you've done wrong, and now you have incentive to do it because you are being given extra points for correcting it. What we find is that students really take that task seriously. And then if you give similar problems to students on the final exam, that's what we are calling post, you can see that students, on similar types of problems, didn't do as well if they were in the low group in the midterm, and here they did significantly better. And similarly, in the medium group, you can see the comparison group didn't do as well as the incentivized group. Of course, students who had done very well the first time, they didn't benefit very much from correcting their mistakes because there was not much to correct. But notice that this means that we are really helping students who didn't do well, and just giving them correct solution doesn't mean that students will engage with them in a meaningful way. And in fact, when we interview some of the students who actually had not corrected that, who didn't do well the second time, they said, oh, I don't like to look at the solutions if I do poorly, or I don't think that those kinds of problems will again come on the exam, so I just ignored those kinds of things. But the truth is that students should be actually given opportunity to build a knowledge structure of physics, and not like this is not the material for the exam, or I don't expect it to come on these types of problems to come on the exam because of the fact that they were on midterm. And so basically, if you give students incentives to correct mistake by giving certain amount of points back and then give them the correct solution, that productive struggle that students go through really helps them learn the material so that they can actually do much better on transfer problem if they use the same concepts of physics. This was true in introductory physics, and this was true in advanced physics, quantum mechanics. So let me now actually talk to you about a third research study, and this focuses on improving students' conceptual understanding of quantum mechanics. So we all know that classical and quantum paradigms are very different, because in class, there's a lot of people have actually documented difficulties that students have with classical physics, classical mechanics, for example, because oftentimes the kinds of notions that people have from everyday experiences don't conform to the laws of physics. Like, for example, people think if an object is moving at a constant velocity, it must not have a net force on it. It must have a net force on it, but we know that it should not have any net force on it. So these kinds of things are very challenging for students, and you need to think carefully about how we can help students with these concepts. Similarly, Newton's third law. People think huge trailer truck must exert a larger force on the small car, and it's really difficult to actually help students with these things because these concepts, these ideas are so ingrained, and if they are not actually brought out meaningfully in the curriculum, they stay there. Now, what about quantum mechanics? Well, it turns out that even if students have a good understanding of classical mechanics, what we have found is that advanced students struggle in learning quantum mechanics. because now, position and momentum are no longer deterministic variable, but they are actually operators that act on states in Hilbert space. And as they say, in Hilbert space, no one can hear you scream. So students have a lot of difficulty, and what we have found is that unless we give them a good opportunity to build a good knowledge structure of quantum mechanics, because even quantum paradigm has a very well-defined structure. And so we can help students, but we need to really merge the conceptual and quantitative aspects of quantum mechanics, because what we are finding is that faculty are not, who teach quantum mechanics are not really helping students with the conceptual aspect. They are often only focusing on helping them do problem solving, but then their knowledge is very superficial and they are not really able to actually answer any conceptual question about quantum mechanics. And that kind of knowledge is not really functional understanding, something that will stay with us, with the students. It will get shampooed out right after the final exam. So, a while ago with my colleagues, Mario Belloni and Christian, we actually wrote a Physics Today article in which we came up with a taxonomy of the kinds of difficulties students have in learning quantum mechanics. So let me give you a couple of examples. So this one is talking about and these studies are done with more than 200 students in the US from 7 to 9 different universities, depending upon which study, because there were 2 different studies that we had done, one with upper level undergraduates, one with graduate students, very similar responses. So basically, what we do is we ask students, if you have a quantum state or wave function, which is a linear superposition of ground state and first excited state as given like this, what is the probability of measuring different values of energy? So this is the ground state, this is the first excited state. So, some people gave this notation, some people gave it in this notation. What we found is that, those more than 200 students from 7 to 9 different universities, 67% of the students provided the correct response and said that 2/7 is the probability of measuring the energy E1, the ground state energy, and 5/7 is the probability of measuring the first excited state energy. But when the second part of the same exact question was asking about expectation value of energy, and you can see that student response suddenly is now 39% correct. So suddenly student performance has gone down significantly, even though these are part A and part B of the same problem. So what happened? What we find is that, expectation value, students are answering this question in a very algorithmic way. They're saying expectation value of energy is integral psi star h, the Hamiltonian operator psi. And, many a times, when they are actually doing those kinds of integrals, some people forgot that there was an integral involved. Some people forgot the orthonormality relation. Some people, make some other kinds of mistakes. And so, finally, only 39% of the students provided the correct response. Now, the easier way and conceptual way to answer this question would be to actually say, if you can use your answer to the first part and say expectation value is the average value of a large number of measurements made on identically prepared systems. So that means if the probability of measuring E1 is 2/7 and probability of measuring E2 is 5/7 and all the energies is 0, then the expectation value, which is the average value of a large number of measurements on identically prepared systems, will be 2/7 times E1 plus 5/7 times E2. Very, 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 very few students use this approach. So that means majority of students, regardless of the instructor, regardless of the textbook, are being taught just an algorithmic approach to finding expectation value that oftentimes is very mathematically complicated, and students make some mistake or the other and get the answer wrong, as you can see over here, as opposed to being taught conceptual thinking and how you can actually answer these kinds of questions without doing complicated calculations. Similarly, here I'll show you something about a question that was asking all these 200 plus students from so many different universities: is the probability density dependent on time if the initial quantum state is this linear superposition of ground state and first excited state? And the correct answer is yes, it is. because the probability, the time dependence of state psi1 will be e to the power minus I even t over h bar, and phi2 will be e to the power minus I e2 t over h bar, and probability density will be the absolute square. And so, you'll get those cross terms, and the time dependence doesn't cancel out. Now, again, you can see only 43% of the students provided correct response. The rest of the students oftentimes had this difficulty that they confused stationary state or energy eigenstate with this linear superposition of energy eigenstates, and they thought that the probability density does not depend upon time. Now notice that, it is not students' fault, because if we are spending all of our time in a quantum mechanics course teaching students about H psi is equal to E psi, the time independent Schrodinger equation, as opposed to IH bar del psi over del t is equal to H psi, which is the time dependent Schrodinger equation, which is really the most fundamental equation of quantum mechanics, it is not surprising that all students can think about is the solution to the time independent Schrodinger equation, the energy eigenstates. They cannot think about these linear superposition. And that is a huge disservice to the students, considering this century is going to be the century of the second quantum revolution. And the second quantum revolution that is, that is now going to give us like quantum computers, next generation of quantum sensing and quantum communication devices and networks, that is totally dependent on, superposition, understanding quantum superposition, understanding entanglement where you have more than one, qubit. And the point is, if we don't actually focus on these and just keep teaching them about, oh, let's solve like hydrogen atom, let's solve infinite square well, finite square well, delta function potential, and harmonic oscillator only for A psi is equal to E psi, and nothing beyond that, students are never going to actually develop a good understanding that really there is time dependence to this linear superposition that doesn't actually go away. And so, regardless of the instructor, we found that the kind of difficulties that students were having were universal, similar to the kinds of difficulties that introductory students have, And so the question is, what can we do? And so we are developing these research validated learning tools, which are developed using iterative process, where we think carefully about the learning objectives, we think about students' initial knowledge, what common difficulties they are having by doing research, giving them written tests with open-ended questions, doing individual interviews with students. And then we develop these guided inquiry-based teaching learning sequences or other kinds of learning tools. And, we try to make good connection with where students' initial knowledge is and build on it meaningfully. Remember, I said impedance matching is really important, and that's what I mean by being in the zone of proximal development, because, Vygotsky was a Russian psychologist, a social psychologist, who talked about this idea that you really need to be in students' zone of proximal development and know about what students' initial knowledge is in order for you to be able to build on it meaningfully. So it's basically the same idea as making sure that you do good impedance matching, because otherwise, students are not going to meaningfully learn anything. So one of the learning tools we are developing are these quantum interactive learning tutorials, or quills, and they are based on findings of research, and they actually build on students' prior knowledge, and they bridge between the gap between quantitative and conceptual aspects of quantum physics, and they often incorporate computer-based visualization tools, which we adapt from other places. And they actually keep students actively engaged. And each of these tutorials comes with a pretest that you can give after your traditional instruction. Maybe you're doing lecture, then do the quilt, which you can actually even have students work with other people, because that's what I strongly recommend you do, because students can learn a lot from each other. I'm not going to talk about, students working with each other today, but my own research shows that students actually can co-construct knowledge. By co-constructing, I mean you're not there to help them, but two students working together in 25 to 30% of the cases, when neither student individually knows how to solve those problems, they can actually do it correctly working with other people. This is what I call co-construction. By the way, the post-test is what happens after they have engaged with these quilts. So let me give you an example of like time dependence quilt. And, so again, in the pre-test, students might be asked, after traditional instruction, does the probability density depend upon time for a stationary state or energy eigenstate? And in that case, it doesn't, because time dependence is an overall phase factor that cancels out when you take absolute square. But then for this kind of a linear superposition, it does depend upon time. But if the student says it doesn't, because all they can think about is the stationary state or energy eigenstate, because that is the only thing that is actually covered in their course mainly. So that's what's stuck in their brain. And seriously, as I said, if this is what we are teaching them, we need to think carefully about, are we doing, a good job of helping students think about things beyond the stationary state? What students find if they said, oh, the probability density doesn't depend upon time. I'm showing you these time-lapse pictures. This is psi star psi, probability density, and this is the position. And you can see that at this time, it looks like this for this state. Another time, it's looking like this. At another future time, it's looking like this. At another future time, it's looking like this. So students now have a cognitive conflict. If they're like, oh my gosh, why does the probability density depend upon time? I'm seeing it evolve. They're going to see a simulation where they see that it actually evolves in time. And the rest of the tutorial is going to help them understand why eigenstates of the Hamiltonian, that is stationary state or energy eigenstates, are really special when it comes to the time evolution issues, because the Hamiltonian of the system is what governs the time evolution of the system. But when you look at linear superposition of these stationary states, then the time dependence of the state is going to be non-trivial, and the probability density will depend upon time. And then students actually work through examples in many different contexts. Some of them are in a harmonic oscillator context or infinite square well context, so that they see that it doesn't just apply to one kind of potential energy, but this is a universal thing that applies to all the cases in which the Hamiltonian doesn't depend explicitly on time. So you can see that, like here I'm showing you for different kinds of tutorials on different topics, like how the students did after traditional instruction and how they did after engaging with the quilt. And you can see the performance after engaging with the quilt is much better. So this is something, if you're interested in, they're all there on the FISPort website. If you can't find them, let me know and I can send it to you. I mean, even topics like quantum key distribution, this is something that people really are excited about, because especially with the second quantum revolution, people are wanting to know more about quantum communication. And there is no classical way to share a key for encrypting and decrypting information, that if you and I were never going to meet in person, there's no way for us to have this shared key that nobody else has, because somebody or the other can always hack it and we may never figure it out. But quantum mechanically, there are these protocols that is, that we can use that actually clearly can tell if somebody was eavesdropping. And so that's a really good thing, because that means that, like the security of these encryption schemes is strengthened. So this is a thing that we just published a couple of years ago in Physical Review, Physics Education Research. If you're interested in any of those things, please let me know. We also have developed a lot of multiple choice questions on these things, which are conceptual in nature. So if any of you is interested in using it as a peer instruction tools in your class, where you can have students do think, pair, share. So think about it individually, talk to a person next to you, and then have a class discussion. I can send it to you because we have it for a full year quantum mechanics course. And here I'm just showing you data for infinite square well using these clicker questions. Well, I call it clicker question, but you don't need to use technology. You can just have them be done as think, pair, share. Think about these questions yourself that you flash on a multiple, on your screen. Have the students talk to each other and then have a discussion in the class about it. And you can see that this red thing here corresponds to the class in which no clicker question, no peer instruction tools were used. These think, pair, share questions were not used. And these other two classes, think, pair, share questions were used. And you can see that the student performance in these blue and yellow classes is significantly better related to these infinite square well issues. So I think that, again, if you're interested in any of these, please let me know. I want to now move on to talking about issues related to equity and inclusion. And we have done a lot of research in this area also. So if you're interested, just let me know. So let me actually tell you about a few research studies that we have done related to improving students' self-efficacy, sense of belonging, and intelligence mindset in introductory physics. So what is the meaning of self-efficacy? It's the belief in students' capability to succeed in a particular task, course, or subject area. And it can impact students' persistence and engagement, and it can affect their performance in physics courses even after you control for their prior knowledge and skill. And it can impact the time on task, and it can also impact the effectiveness with which students engage in learning. Because notice that cognitive science says that your working memory only can keep 5 to 9 chunks. And if some of those chunks are being taken up by the anxiety of the situation, then you have less of those things available for problem solving and learning. Moreover, the anxiety can also make you procrastinate, and you may not want to engage with something that you know you're not good at. So actually thinking about these things is extremely important. And if you look at our discipline, physics, this is the famous Solvay conference, Sixth Solvay conference from 1927. And one of the things that you see here is that everybody here is actually, all the people are males. There's only one woman, Marie Curie, here. And that means, like if you really think about women in physics or other underrepresented people in physics, first generation college students, low income students, people who have not traditionally gotten an opportunity to be there in America, racial and ethnic minority students, what you see is that those people could be having what people call stereotype threat, and if you don't provide an environment where they feel like they belong, where they feel like they have what it takes to excel, they are more likely to actually, have, issues and anxieties, and they might even drop out even if they're doing okay. Because, in fact, I'm going to show you data from my own classes, but this is basically a picture from a recent physics conference in the US, and it doesn't look I don't see very many women here either, actually. So let me show you some data from our own courses to show the inequities in the current situation. So here I'm showing you data from very, very large introductory physics courses. We teach classes with more than 200 students. This is, and these are mandatory courses for engineering majors and and also physical science and math majors. So this is physics 1 and physics 2, right? And what I'm showing you on the vertical axis here is what is student self-efficacy at the end of the course. And here I'm showing you like their grades, the grades that they got at the end of the course, right? And the top thing is for male students and the bottom one is for female students. And what you see is that at the end of physics 1, women with A grade have the same self-efficacy as men with B grade. By the time physics 2 comes, actually, female with A grade have the same self-efficacy as men with C grade. So in fact, the self-efficacy difference about how good they are at solving physics problems has actually increased. And people who are actually marginalized, traditionally marginalized in physics, like women, actually are feeling even worse about their ability to solve problems, even if they are getting A grade. Their self-efficacy here is statistically indistinguishable from, men with C. Now, notice that what is important is not just the grades that you're getting. What is also important is your self-efficacy. If you don't think that you're good at something, you are actually going to drop out of that discipline and you may not remain in this discipline. And actually, these are some of the comments that we hear from women, have pretty low self-confidence. When I see how other people are so smart, other people understand more. How do you know that other people understand more? They could just be showing off. But the thing is, nobody knows. If you don't create an environment where struggling is actually something that is valued, you tell students to pat on their back and tell them that this is a good thing, because that's why they are in college, because it's all about working hard, working smart, taking advantage of all the resources. Even Einstein said, if you haven't struggled, you have not really tried to learn anything new. So telling students that struggling and failure in solving problems is not really a failure, that is actually part of the learning process. You learn from all of those things, and that's how you get to the next step and to the next step. So it's really important to embrace your struggle and use that as a learning opportunity. Unfortunately, we are not doing a good job of any of these, and I'll show you data here. So these are again data from a very large number of students. And, in the horizontal axis, I'm showing you, the year that they are in college. And vertical axis here, you see the mean GPA, grade point average, or the average STEM GPA, their GPA only in science courses and engineering courses. And the top thing here, purple one, is showing what are the grades of women who actually did not drop science and engineering. In this case, it's computer science and engineering majors. So the ones who actually declared it and who actually finished, these are the women. The green ones are men. What is shocking here is the bottom two curves, because you see that the bottom blue curve here is showing women who dropped out of computer science and engineering, and this red one is showing men who dropped out. And you see that there's a huge difference in the grade of men and women who actually decided to drop out and did not want to pursue this. Why? They must have low self-efficacy. They must have low sense of belonging. Now, there are different ways of thinking about it. You can either say, oh, maybe these people actually didn't really want to be there. So after a few years, they realized they wanted to do something else. But that is wrong, because we didn't create an environment where they felt like they belong, where they felt like, they had high self-efficacy, where they felt like they had growth mindset. We are not inculcating growth mindset among students so that students realize that it's not some innate or immutable thing that makes you good at physics. It's really about working hard, working smart, taking advantage of all of your resources, and patting yourself on the back when you're struggling, because that means you're on your way to learning something new. And so you can, and in fact, this is for computer science and engineering. The trends are similar for math and physical sciences. I also wanted to show you data on percentage of students who drop a particular discipline after they declare a major. And you can see our discipline, physics, if you look at all students, 38% of the students are dropping out. If you look at, underrepresented minority students in America, you see 65% of the students are dropping out of physics. No, these are things that we should be actually feeling really bad about, because these people loved physics, and this is the situation. So that means there's something wrong in what we are doing. And I must actually also, I don't know if you read this book called The Only Woman in the Room, which is a memoir written by Eileen Pollock, who's now an English professor at University of Michigan, Ann Arbor. And she actually was the first woman to major at Yale University in physics in the 1970s. And in this memoir, she says, the undergraduate research was mandatory at Yale. She said, no professor ever encouraged me or told me that I was doing a good job, even if she was getting good grades. Nobody told her that she was doing fine. Nobody told her to go to graduate school. No, that means to do PhD. Nobody actually, she said that undergraduate research was mandatory. And she said that when she took a theoretical work with some professor, and when she said that she solved that problem, she said, I felt triumphant. I ran to that professor's office because I thought he'll tell me, Eileen, you should go to grad school. This is so awesome. Guess what happened? When she knocked on his door, she showed him the work, and he's like, okay. And he went back to doing whatever he was doing. And she said, from feeling triumphant, she felt like she was at the bottom of the ocean. Because she thought maybe this problem was like really an easy problem that he had given me. And, she said, should I still ask him if I should go to grad school? Because she was the only woman and she was not sure about herself. She was always questioning whether she has what it takes to excel and whether she was really cut out to be there. And if nobody is recognizing her, nobody is affirming her, she was really not sure. And she said, no, if I need to ask, then I'm not cut out to be in physics. On the other hand, her English professors were always telling her that she was good. So she did her graduate work in English, and then she became an English professor. What is interesting is that, when she went back in 2016 to write this book, what she met with that same professor who was her undergrad advisor, and 30 years later, she's so much more mature. She asked him point blank, what did you think about my undergrad thesis? And he said, oh, Eileen, I still remember it. Not that many people do theoretical work. I remember you had done an exceptional job. And she said, I got teary-eyed. I really said, really? Why didn't you tell me then? I would still have been a physics major. I really miss not being a physicist. Physics is my first love. So all of those people who are dropping out, of physics, they actually wanted to major in physics, and yet we made them actually leave. Okay, I think I'm really running, so I'm going to just skip these data because I'm probably already behind, but let me actually quickly tell you something that we do at least at the beginning of the course that helps a lot. So what we actually started doing in our courses at the introductory level, this is something that we started out as a control study, and these studies have been done a lot at Stanford University by people like David Yeager, Greg Walton, Jeff Cohn, and you probably have heard of Carol Dweck, all of these people. So we actually had some colleague in our psychology department who actually was from Stanford. And so he actually helped us implement this thing, which is just a 25-minute activity that you can do at the beginning of the course. And basically 3 instructors participated, and in some of the recitation classes. So what we have is we have these classes with more than 200 students, and then they're divided into these small problem solving classes, which are only 40 students each, and there they do problem solving. So at the beginning of the semester, some of those recitation classes, this 25-minute activity happened, whereas in the other control group, none of these things happened and students just kept doing problem solving. So what was the goal of this 25-minute activity? We said to we wanted to convey to students that struggling is the only way to learn something new. So students should be proud of struggling because this means that they are already on their way to learning new physics, and they should be proud of doing challenging problems, pat themselves on the back, and they should work with other students. They should go to the office hours of their professor. And the idea is that it will reduce anxiety, reduce procrastination, increase enthusiasm for solving challenging problems, and ensure that the limited cognitive resources are used for problem solving and not for the anxiety. So notice that basically in this activity, and since I'm running out of time, let me just summarize it for you quickly. So in the experimental group, basically what we do is, like this in this 25-minute activity at the beginning of the semester, right? The instructor will say, physics department really wants to understand what your concerns are about being here. And notice that these are also first-year students who are science and engineering students. All of them have to take 2 semesters of physics. And why don't you write on the sheet of paper what your concerns are? And students write a lot. And then within 10 minutes, we say, okay, stop. At this point, we show them testimonials on the board, on a PowerPoint from a lot of past students who have done extremely well, but they also had similar concerns. And some of them are female names, some of them are male names, some of them are minority names, some of them are majority names. And they're all sort of saying the same thing in their own ways. All of them are saying, I was really concerned about how I was going to do in this physics course, but then I realized it was really about working hard, working smart, taking advantage of all the resources. I started working with other people. I started patting myself on the back, realized that no, it's not going to be that everything should come to you naturally, immediately. Keep struggling, keep thinking about it, keep building your knowledge structure. And in the end, lo and behold, I ended up doing really well. After these testimonials, like from 5-6 students are asked to sit in groups of 5, get together in groups of 5 and discuss what they wrote on their sheet of paper. And why don't students realize that struggling is normal? And why don't students realize that struggling is actually good? That's how you learn new things. That's why you are in knowledge. And also, how will things be different when you are actually, in your 3rd year or 4th year? Notice that when you say, why don't you realize that, that struggling is normal, we want students to buy into it. So students had great discussion for 5-10 minutes in those groups, and then we asked each of those groups to report out. And what they saw is that all of the groups were pretty much saying the same thing. And what we saw is that at the end of this activity, students felt so good that some of them even came and especially women came and said, I'm so glad that you said this. By the way, the instructor also talked about their own adversity. They said, oh yeah, I remember when I was in college, I used to struggle with these things too. And I used to embrace my struggle and use that as a learning opportunity. This was just not true for me. It's true for all of my colleagues. I talk to my colleagues all the time. This kind of thing is true. And we are, the same thing happens in our research also. And in the control group, as I said, they had normal recitation with just problem solving. So I'm not going to go over all the activities here, but I'm happy to send them to Sapna, if anybody is interested in the script. I just wanted to show you here that when we look at the performance of men and women in the social belonging group, there is no difference in the performance of men and women. On the other hand, in the control group, there is. Also notice that, when you do similar analysis by race, you find very similar thing. By the way, the same colleague who helped us do it in physics also did it in biology. And even there, they find benefits, especially by race. And this is something that has already been published, so I'm also happy to send this to you. But I want to close by saying that, so we need to think, for the longest time, we have actually thought of ourselves as, instructors who should be helping students develop efficient problem-solving skills, effective problem-solving strategies, be able to transfer their learning from one context to the other, help them develop a robust knowledge structure. Yes, of course, those are our responsibilities, but we also should think, it's really important that we think of ourselves as coaches for all of our students that we are teaching, and coaches should not just focus on offense, but they should also focus on defense. When you're teaching somebody to play, chess, you will be teaching both. And so what do I mean by defense? I mean, it's our responsibility to improve students' sense of belonging, their identity as people who can excel in physics courses, have them develop a growth mindset. That means intelligence is not something that is immutable, but your brain is a muscle and it can grow by working hard, working smart, taking advantage of all the resources, and also help them develop high self-efficacy, belief about how good they are in solving physics problems. Because as I said, these things are important in themselves, and it's not just your grades that matter, and people will leave the discipline and will actually miss out on the talents of a lot of people who actually, whom we might not be helping because they are from traditionally marginalized group, because those are the people who are more likely to have these kinds of issues. And notice that if we could actually help them with this, they would also be more interested in learning physics, and they would also have higher achievement goals, because these things will actually create a safe environment in which they will not feel judged, and they will also want to participate with other people in learning. So in fact, we actually also published some results that I'm happy to send to you, which shows that active learning in an inequitable learning environment where you don't actually focus on these kinds of things mainly helps everybody, but it disproportionately helps men, because those are the people who dominate in group discussions and everything else. So what you see is that the gaps between men and women actually increases as opposed to decreases, even though everybody learns more. That is not a good thing. So if you actually create an equitable and inclusive learning environment by actually doing the kinds of interventions that talked about, and you will actually see that women and other minority students are not going to have the same kind of concerns. Oh, if I speak in this group discussion, and if I don't say something correct, will people think that I'm not, will I be speaking for all women, that women can't do physics? Because there are lots of stereotypes about all kinds of things, and those people are already stressed about those things. So we need to dismantle those stereotypes. We need to actually make sure that students actually are able to talk about what they are struggling with, and feel proud of not knowing, and pat themselves on their back and use that as a stepping stone to learning new things. And I also wanted to say that most importantly, your mindset about your students' potential, and what your mindset is about what you think about men and women and other students in your courses, makes all the difference in terms of how students do. In fact, there was a study done with 150 faculty in science at Indiana University, in which more than 10,000 students participated. This was published in 2020. And what they gave to professors a few questions like this. To be frank, only 20% of the class should, is capable of doing physics. The rest of them should, or science. The rest shouldn't be there, or, things like that, because those things convey fixed mindset about your potential. Or underrepresented minorities shouldn't be doing as well as majority. If you agree with these kinds of statements, you have fixed mindset about students' potential. And if that is the case, what they saw is that there was a huge difference in how the students actually ended up doing in those courses, and those professors who had fixed mindset about their students' potential, the gap between minority and majority students was really large, whereas there was very small gap in the professors' classes who actually had growth mindset about their students' potential. So these kinds of things are extremely important. And so remember to actually recognize students, affirm students, and also if we let only some of the students dominate in the class, if three men keep asking all the questions in the class and you let them dominate, that also actually hurts the self-efficacy of everybody else. So instead of letting them dominate, it's better to say, okay, here are some questions, can everybody in the class think about it, talk to a person next to you, and have a different part of the class actually tell you what they're thinking. And also, I'm not telling you to cold call students, because that may not be the best thing. But when you have had students think, pair, share with each other, and then you ask a group to think about it, and every time a different group, that would also be much more equitable. And similarly, if you're having office hours when students come for help, again, make sure that you treat students equitably and not let only a few students dominate, and also ask questions that are not even relevant for that class, because students are there to ask questions about the course and not about your work in black hole, because those are all things that actually have happened. We have done 70 interviews one-on-one, which are each 1 hour long, to ask students about their experiences. We have heard a lot of those kinds of things as well. So it's really important to create an environment where all students see that they have potential, and it's really about working hard, working smart, and failure is not really failure, but a stepping stone to learning. So one should be embracing their struggle and patting themselves on the back. And you can see that all of your students then will do a lot better. In fact, I can also send to Sapna a video from this Ohio State faculty, Roland Kawakami, who's talking at a conference about how doing this short intervention at the beginning of the course actually changed his life. He's like, I basically am a totally different person, and my relationship with students is so much better now because of the fact that I actually started doing it. So I would like to stop here and take any questions you might have. Thank you.
Thank you very much, ma'am. So this talk was totally remarkable, actually, and your expertise, knowledge, and passion were evident in every word you spoke. So we are grateful for the insights you have shared with us, like conceptual knowledge and problem solving should go together, and students should be given opportunity to build the knowledge structure by solving the problems, or it is co-constructing the knowledge. And also we should focus on the mindsets and of students, and that is important actually. So I am sure that the participants must have enjoyed it. So I would like to request Pradhan sir to share his views. Pradhan sir. All right. Okay. So yes, sir.
Very nice. Can I speak?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Okay. It was really enjoyable because I could see the passion which probably Chandralekha Madam brings into her class from the kind of speech that, from the kind of lecture that she gave us, because she was so passionately interested in the talk. What I would say also is this, that, she brought out the importance of, especially in my opinion, of what we would call scaffolding, and how important scaffolding is, especially with respect to even the affective aspects of teaching. Because, very often we professors go to the class and we do just procedurally right things and we expect everything will really happen. But that's not the case that you really brought out so well, because it's very important to actually know how the students are learning and how we can actually sort of, guide and push them into sort of interacting with their own learning. That is what I think you wanted basically to say, and that is what your research really has emphasized. And I thought, especially in India, when we teachers are embarking on a very important aspect of physics education in the classes, I think we'll have to bear that in mind. That, we should not be mechanical, because, very often we are mechanical and we're good at it, but we don't really sort of, face the real truth that we might go to the class and the students may not really end up the class, learn nothing. Why does that happen? That I think we need to really think about very deeply. And you brought out the importance of reflection in that sense, reflection on the part of a teacher. And the kind of, one would say, scaffolding that is needed And I think that is what you underscored. And I believe that, this has been, we would really like to have your, sort of papers produced in our IIPT bulletin and so on. And let's see whether that can happen. I would request our editors of IIPT bulletin, which we publish regularly every month or so, to sort of record the kind of research that you have done on physics learning and physics teaching. So thank you very much. And on behalf of IIPT and on behalf of, perhaps I would say, the entire physics teaching community in this country, thank you very much. And I hope, we can take something from you and actually practice it, so that we make a difference not only in our classes but with respect to physics education in the entire country. So thank you once again, madam. Thank you for coming, and thank you for joining us across the seas or so. But we'd love to have you again, for such kind of discourse and such kind of discussion. Thank you once again.
Thank you so much. Thanks a lot.
Thank you. So now we can have questions actually. Participants, if you have any question, please raise your hand, or you can write it in the chat box.
There's already a question in the chat.
There's one question actually, ma'am. One question.
Yes, please.
Yeah, the question is, at the basic level, what makes quantum mechanics difficult? Ma'am Meera is asking this question. Second question is, using simulations, which will put students back to visualizing, which I think is one reason why quantum mechanics is difficult. Is it a good approach? So Ma'am Meera is asking these questions.
Yeah, thank you. So I think that these are all great questions. So I would say that, when we are actually living, when you get used to classical way of thinking about things, and the quantum paradigm is very different, that produces a challenge, right? As I said, when you start thinking about position and momentum, these things are no longer deterministic variable like they are that evolve, like when you actually tell me what forces are acting, I can actually tell you the trajectory. It is not like that. We are talking about wave function, and, that wave function has all the information about the system. We don't know before we measure something, we don't know what what would be the different physical observables that, we only know the probability of those things, because basically the wave function just gives us different probability of measuring different outcomes, right? So this idea that the measurement outcomes are not certain, and you only have different probabilities of measuring different things, those are all things that make things very difficult, right? Similarly, when you go, and so this idea of, when you go beyond like one qubit, when you start thinking about entanglement, there isn't any classical analog of that kind of thing, right? You have classical correlations, but that's not really the same as quantum entanglement, in fact, that is the reason why even Einstein was very puzzled about it, right? So if you think about EPR paradox, Einstein, Podolsky, and Rosen paradox, basically he was really puzzled about how is it that, two things that are entangled could be really, really far away, and somehow when you measure, let's say, something in one of them, instantaneously, you have collapsed the state of the other one, so these ideas are very challenging because they don't kind of chime with the kinds of things that we are used to in classical ways of thinking. But notice that the good thing is that, the quantum paradigm is very well defined, and at least, it has never been shown to be wrong. So that's the beauty of the thing. All the experiments show that this is a very robust paradigm. So yes, we are working with our wave function as a unit. So we are preparing our quantum state to be something, and that has all the information that can glean out of this thing. And yeah, it is going to be very hard for us to think carefully. For example, in the second quantum revolution, we are thinking about what are the algorithms that we can actually come up with that, what problems can you solve on a quantum computer much better than a classical computer. It's true that, physicists and chemists are very excited about being able to solve time-dependent Schrodinger equation itself, right? Because the thing is, a lot of problems are very difficult to solve on classical computers. But, thinking about all the constraints of this paradigm where you have a wave function that has all the information about the system, but then when you actually do a measurement, you collapse your state, and those kinds of constraints will actually mandate what kinds of other algorithms we can actually come up with that would actually help us do things on a quantum computer much better. For example, like you already have heard about Shor's factoring algorithm or Grover's algorithm for, searching unsorted data. Those kinds of things, Shor's algorithm gives us exponential advantage, whereas Grover's algorithm gives us, quadratic advantage. But these things are all algorithms that really take advantage of the fact that the quantum paradigm is very different, and we only are dealing with this wave function, which is like a linear superposition, and we don't know each of the observables are not well defined, but we know what the probability of measuring those things are and how they are going to evolve if we know the Hamiltonian of the system. So this is a challenging thing for students, and that's why we need to think very carefully about it, about how to help students. And yes, I totally agree with you that simulations are great. There aren't that many hands-on, because any kind of concrete experiences you can provide to students would be very helpful. But, there aren't that many hands-on experiments that are at least not inexpensive ones that you can do. And so using simulations is a really great tool, because any kind of concrete experience really would help students think through these things in a meaningful way. So thank you.
Dr. Singh, I am Dr. Meera from Department of Physics, Bangalore University. I was the one who asked the question. You're here?
Yeah, please. Nice to meet you.
We have a good physics education group in the university. I'm very keen on your work. I'll get back to you a little later. I would be very interested in trying to see if we can try and test some of your tools with our students in India. So I'll get back to you. It's very nice listening to you. I have been aware of your work all these years. It's very nice to see you also. Thanks
Thank you so much. Yeah, please get in touch. Thank you.
Good evening, ma'am.
Yeah, please.
Hello, am I audible?
Yeah.
Mahato, should I proceed?
Yeah, please.
Okay, ma'am, I'm Dr. Mrityunjoy Mahato from Nehu, Shillong, India. Actually, since you are talking about the second quantum revolution, so in this connection, I have some queries. We are listening this quantum technology, quantum devices, a lot of things. But we have a little bit confusion that what are quantum technology? Basically, in our understanding, maybe after physical geometrical optics, when it is starting the physical optics, interference, diffraction, then laser spectroscopy. In our understanding, it is all quantum science or quantum related devices. So what actually the quantum devices nowadays people are talking? It's a very earlier concept only. Precisely what nowadays is talking, quantum devices, quantum technology.
So you are absolutely right that, for the last 100 years, right? Remember 1901, Planck came up with his thing, and, so the last century was like the first quantum revolution. And yes, we know about lasers, we know about nuclear energy, we know a lot of, the computer, the transistors, all of those, the transistors are the ones that led to a major revolution also. And so everything that I'm using right now to communicate with you, we can call that like the product of the first quantum revolution. Lasers are first quantum revolution. By second quantum revolution technology, we mean things like quantum computers. And now you might say, do we have a quantum computer? It turns out that IBM, Google, Microsoft, and many other companies, Honeywell, called quantum. I mean, basically, many companies are actually trying to develop quantum computers, and those things are like quantum technologies of the second quantum revolution. But notice that we don't have scalable quantum computers that will do useful things. So all of those quantum computers, even if they say, oh, we have a 100-qubit quantum computer, 200-qubit quantum computer, those quantum computers are not really very useful to do useful things. Even if they say, oh, we have actually, come up with quantum supremacy, and Google has shown that, like quantum computers can do something faster than classical computer. Those problems that they're doing are really silly problems, that are toy problems, not really any problems that you would really want the computer for, right? So for example, the credit card transactions that we are doing on the internet, no time in, in the next few years, like you would think that a quantum computer will be able to break that particular RSA protocol that makes it safe for us, with 512-bit encryption or something to do those transactions. So the thing is, I do not believe that in the next 5 or 10 years we are going to necessarily have a scalable quantum computer. So and the main problem here is quantum error correction, right? I mean, like just the issue that we were earlier talking about, like the major issue, and this might actually go on for the entire century. This entire century is, how do you correct quantum errors? Because when I talk to my mom in India, like I basically use, there are errors that are being corrected all the time, right? And so the thing is along the way. But the point is, like in quantum mechanics, we are saying that, when you do measurement that collapses the state, that changes the state. How do you actually do something in a way where you only gain some partial information, but you don't really change what your quantum state really was? So quantum error correction is a huge problem. The other thing is that decoherence is a much bigger problem in quantum computers than classical computer, because classical computer, everything works on 0 and 1. And maybe it's like, the voltage across a capacitor that you're using as a bit. But the point is, like, turning a 0 into a 1 or a 1 into a 0 is a very difficult thing. So if I come back tomorrow, my computer will still pretty much be in the same state. Errors don't come up that often. On the other hand, when you are saying that your quantum bit or qubit, that is behind this quantum computer is a linear superposition of 0 and 1, like, so it's, some constant times 0 plus some constant times 1, and the only constraint is that those constant squares, absolute squares, should add up to 1. Even small changes in those constants can change the bit, can change your quantum state, qubit. And so the point is that quantum qubits are much more susceptible to errors because of the fact that those coefficients, in front of those 0s and 1 can change, like, just a little bit, and that's no longer the state. So the thing, and whether you're talking about electromagnetic radiation, and that's why you see that all the quantum computers right now are at very, very low temperature to make it easy to actually, so that the decoherence is low, because otherwise it's a huge issue. So notice that you want to minimize decoherence. At the same time, you want to maximize, you want to actually figure out how to correct error so that, you don't have those kinds of issues. And it's not going to be easy. We are making progress, and that's what's preventing us from making a scalable quantum computer. And if you just come up with too many qubits, then it doesn't necessarily mean that that's a good quantum computer, because of the fact that, the errors are also multiplying. So we need to think very carefully about how to do these things in a systematic way. And also, I must say that quantum computing is not the only quantum technology. There are 2 other kinds of quantum technology, like quantum communication and quantum network, so quantum communication, for example, China is the country that is ahead of everybody in this game. Like you heard about, like in 2018, November or December, like they even came up with, this how to do teleportation, for example, right? So you actually can do, you can think about quantum communication, quantum network, and we could have a quantum network in the future. And in the future, it might even be that quantum computers and quantum networks are going to be actually connected together, because so that we could do things. And it's not like the quantum technologies, like quantum computer is never going to replace classical computer that we are using right now, the computer that we are using to communicate with each other, but certain kinds of problems will be actually much better to do on a quantum computer, right? And the things, for example, as physicists, we are very excited about being able to solve time-dependent Schrodinger equation, because a lot of those things, think about the fact that 100 qubits, 100 electron spins, for example, really the vector space, if you think about the Hilbert space of 100 electron spin, it's 2 to the power 100. That is like, or 300 electron spins, their Hilbert space is 2 to the power 300. That's more than the number of atoms in this universe. So the point is that, 300 electron spins will be able to do things, that there is no way to store that much information on a classical computer, because we just cannot actually store 2 to the power 300 coefficients on a classical computer, right? I mean, that's just like not possible. But 300 electron spins will know naturally how to do that if you know how to gate them or evolve them in time and not have the errors creep up. So notice the other issue here is the quantum technology. The third quantum technology is next generation of quantum sensors. Notice that it's not that we don't have sensors. We already have like MRI machines. We have like, different, LIGO actually uses very sensitive interferometers and things. But quantum technologies where you use the entanglement and other things, very, so again, you can see that we have come a long way. And so there is a lot of hope for making these next generation of quantum sensors. I also wanted to say that, like the reason these quantum technologies, that means quantum computer, quantum communication devices, and quantum sensors are going to be really hard is because of the decoherence issue and because of the issues with measurement, because measurement collapses the state. And so doing the error corrections is not going to be easy. And I also wanted to say that notice that you also want it to be able to actually evolve the system in time. Like a computer is based upon, this computer that I'm using is based on classical gates, those NAND gates, NOR gates, and stuff like that. They're quantum gates too. And you can show that 2-qubit gates like C0 and some single qubit gates are universal for doing any computation on a quantum computer. But again, if you want to be able to gate your system, you're applying some electric field or magnetic field. So it's not like you want to completely isolate your quantum system. So how do you actually gate your quantum system, but keep it isolated so that the electromagnetic radiation and other things don't destroy or decohere your quantum system? So that's the challenge for the quantum technology of quantum computing, quantum sensing, and quantum communication. But this is going to be not an easy challenge, but a fun one, really exciting one. So I'm looking forward to it. Thanks.
Okay, thank you very much, ma'am.
Hello, ma'am.
Thank you.
So quantum devices mean quantum computer, quantum communication, quantum network, quantum sensor. So these are all related to
quantum technologies.
Quantum
of the second generation, yes.
Okay, thank you very much.
Thank you.
Hello, ma'am.
Please.
I have one doubt in this. As you talk about the inclusive teaching method, you have this post and pre-assessment test, and you also said about the think, pair, share thing. But ma'am, when it's come to implementing these things to the large number of students, or having, it's very difficult for you. When you have to complete the material, I mean, what I have the question is, if you have a large group of students.
So, I heard your question, and thank you so much. That's a great question. I would say that, even in a large class, think, pair, share works really well. In fact, you probably are familiar with Carl Wyman from Stanford University. Like he got Nobel Prize in Physics in 2001 for Bose-Einstein condensate. He does physics education research, and he was telling me that, he was trying to do a study to see whether you can replicate some of these studies in large classes or not. And what he found is that, you basically see very similar results whether you have a class of like 40 students or 200 students. So long as you actually think carefully about, setting the norms for your class, and notice that it's really important that you set the norm for your class from the very beginning. So if you start doing these think, pair, share questions from the beginning, even in a 200 student class, it works really well. So I think that, we have not seen any difficulty because, as I said, like, for example, you can actually post a question on the PowerPoint that says, oh, a huge trailer truck hits a small car right after teaching Newton's third law, right? Which one exerts a larger force on, this one on that one on this one, equal and opposite, right? And let the students think, pair, share. And then, after that, you can say, okay, how about somebody from here? What do you think? What do you all think? And if they said, oh, huge trailer truck exerts a larger force, you can say, that is a really great thought. And that's the way a lot of people think. But let's see how this actually relates to the Newton's third law that we were just talking about. The forces should be equal in magnitude and opposite in direction. It's the acceleration of these two things that will be different because of the fact that they have very different masses. So I feel like, it actually works really well, even with large classes.
But ma'am, what about the post-assessment and pre-assessment? Is it possible for you to do it for the large class?
So notice that, unless you're doing it as a research study, you can do it, but if you don't want to spend class time on pre and post assessment, another way to do it is to just do the think, pair, share in class, and pre and post assessment you can even do online. If you make it low stakes, then students are not going to, look up the solution. So don't make it very high stakes. Use it as a formative assessment. So in that sense, because I think that it's not that the pre and post test you cannot do, but it's also if something that takes time. And if you really want to actually say, look, let's just post it on the website and let students do it online or have it be done as a homework, that is another way to do it. But you cannot do that if you are doing a research study. Because in research study, it's important that students actually do it right in front of you.
Okay.
So we have two more questions. Like Professor Ahluwalia has raised his hand, and Shadeen Rahim. So we'll have last two questions from them.
Please.
Shireen, it's me, ma'am. Shireen Rahim.
Okay, then it's fine. Then Ahluwalia sir, please sir, unmute yourself.
Okay, all right. Thank you, Chandralekha. This was a wonderful presentation. Enjoyed it thoroughly. And the one thing which I liked is that you presented yourself, and I think that is a model which is worth following, as a teacher, a physics teacher with an empathy towards her students. I think that was one lesson which we can take from here. Another thing which I really noticed was this, that you already started floating some vocabulary with the quantum mechanics students, where they don't talk about, say, a wave function or a quantum state, but you straight away start talking about a qubit. And, getting them used to all such vocabulary is another step forward here. There is, one very interesting thing which I feel we need to really look at is that when it comes to, doing such education research, physics education research, most often people think that, oh, this is something which should be done in education departments and not in physics departments. When you bring these kind of, strategies in the physics classroom, you are really not doing physics. This is also one of the kind of dilemmas in the minds of physics teachers or the people who want to engage in physics education research itself. And I feel that if you can really address this point also, that will be very good for us, because we have faced it in our own environment as such also. Secondly, you know, with the national education policy coming into picture, I hope you are aware about this, that in India we are talking a lot about National Education Policy 2020. There is a lot of, you know, talk about problem solving, critical thinking, and visual thinking, computational thinking. All these, you know, terms are being put forward, and we are suddenly, you know, finding that people are switching over to this vocabulary also. Now, when we are really talking about this in the Indian context, we know the numbers are overwhelming. I mean, the number of students who come in the class, there is no space to seat them. So most of the students sit outside the classroom itself. Maybe they are not really coming to the class itself. So how to engage with such huge numbers, you know? Coming of the experience of COVID, when we switch to some other such tools, do you think that now post-test and pre-test are very easy to conduct, where you can proctor the students also when they take their tests, and you gather the data from there itself? What is your take on, you know, these developments which have happened in the last 2-3 years because of the COVID itself? Thank you very much.
Well, thank you so much. Thanks a lot. Okay, so with regard to your question about, you know, should this be done in School of Education or in the physics departments, you know, like, I think that definitely you can see that the kinds of things that we do relates to physics, and all the benefits accrue to the physics department. You know, you need access to the physics students. So it doesn't make sense to do this kind of research in School of Education, because then, you know, like, they will not have easy access to students. They will not have, you know, like, easy ways to implement the changes that you actually want to make based upon the research that based upon research finding. So so I can again send to Sapna something that actually was written up, like, I think in the late 1990s, in the American Physical Society. You know, there was a statement from the American Society about this issue. So I'm going to actually send it to her so that, you know, like, she can send it to you, because I think that statement actually addresses this kind of issue and why it should be done in the physics department. Now, in fact, you know, like, after that statement in the American Physical Society, which was I think in 1998 or 99, I could be wrong, it could be 2000, but then in 2006, American Physical Society started this physical review physics education research, right? So that has been there for like since 2006. So you can see that physics, American Physical Society slowly actually understood the value of physics education research being done in the physics department. So I think that, you know, it may take time, but if you keep emphasizing the importance of doing this kind of research and how the value of this research, you know, the benefits are accruing to the students in physics courses, and how you need access to the students in physics, and it's essentially focusing on physics, my guess is that over time, other people will understand that it should be done in physics department. Okay, so the other question that you were asking about pandemic was about pandemic and what its impacts are and things, right? Yeah, so again, you know, I feel like pandemic has definitely, you know, changed things a lot, and students have been really disadvantaged. And it turns out that mainly, by the way, one of the things that my students and I are also analyzing some data here, and what we are finding is that actually women, somehow female students are more disadvantaged during the pandemic than men. You know, that's what we are finding based upon how they are doing in terms of their grades and other things, you know, like compared to before the pandemic. And now, you know, like, I don't know that quantitative data will tell you exactly why, but I can think of a couple of reasons. You know, one is that, you know, maybe if you're actually at home, maybe women were more likely to help out with family things and other things, you know, and because of that, they had less time to actually engage with things. So that could be one thing. You know, because everybody was at home, right, huddled in a small place. The second thing is potentially that, maybe women are more collaborative and they didn't have this, like face-to-face interaction with other students, like that they used to work with on their homework sets and other things. They were more disadvantaged, but I think that all students are disadvantaged, but I feel like, certain students are from certain demographic groups might be disadvantaged even more. And yes, the impact of a pandemic, definitely is huge, all the way from like kindergarten through, every grade that you can think of, because, even in the US, you can see that people, another thing that we see is that during the pandemic, people gave higher grades, and now the grades have come down again. So during the pandemic, like people were deliberately told to be easier on students, and, things were easy. And now the question is, all the stuff that people have missed, people couldn't do as many things on Zoom. And so the question is, what can we do, because of that? So there is definitely a lot of catching up to do because of all the stuff that the students have missed. And it's sort of like a cascading effect, right? Because it's not just like the students in your class, but all of the people who are impacted in some sense, math and science that they missed. These subjects are also very hierarchical subjects. And because of that, like the kind of things that they have missed can really be an impediment. And we need to, again, based upon this idea that we need to actually do impedance matching, it's really important to think about what the student's prior knowledge is so that we can actually be in that zone of proximal development, as opposed to have two orthogonal polarizer be next to each other, right? Where students' initial knowledge is this way and our instruction is perpendicular to it, nothing will go through. So that's not a good situation. So we really want to think about their initial knowledge and build on it in a meaningful way. And if they have been impacted by COVID, then we do need to think about how we can incorporate some stuff so that, like we can actually review some of those things in a meaningful way and build on it so that, their learning is meaningful, as opposed to them just memorizing something and then, vomiting it, but not really understanding what's going on. I also wanted to say one thing about the pandemic that really struck me, because we did do 36 interviews during, after the pandemic to actually understand students' experiences during the pandemic. And this is an article I actually wrote for Times Higher Education. And this was, what we found also is that students were also not wanting to miss the Zoom classes in which the professor was actually starting the class by checking on the students in terms of their well-being. They're like, how is everybody doing? They were also talking about their own adversities, what's happening in their own family. And just spending 1 or 2 minutes doing this kind of a thing humanized learning to the extent that students felt like this was a community that they wanted to be part of. They just went to all of the classes, did not miss anything. And one of the things that they said, that we wish that in our in-person classes also professors come across as more human, because, otherwise they come to the class, it's like, oh, Gauss's law states this, like they start writing, Gauss's law statement, and there's nothing before or after that. And it's like, if they actually communicated a little bit right before that, so even going to the class like 1 or 2 minutes early and just, having some communication with students, like brings down the barrier and reduces their anxiety and makes them feel like you are also a human being, and that kind of like improves the relation, and they want to work harder, they don't want to miss your classes, and they really become invested in what you're doing. So I think that, those were the things that I learned in terms of, what to do about the classes overflowing and stuff. Did I understand correctly? Is that what you were saying?
Yeah. Yes. For example, the numbers here are too big. You were talking about 200 students sitting in a classroom. Sometimes we find that we have 200 students, but we do not have 200 seats in the classroom to seat them. So that is a big issue also. And in that context, when we start talking about, these kinds of reformations, they don't really reach out to the students. They just remain on paper, and we say, okay, we are trying to bring in something new, which looks very theoretical, but when it comes to implementation practically, it looks as if nothing is really going to change on the ground. That is what I was actually trying to say. And maybe then we have this hybrid mode, which can really connect all these things together. For example, when you are using Clicker Classroom, and here you are using, say, Google Form, I think both amount to one and the same thing, because you can draft your questions there also and post them. At least one question in one classroom can serve a big purpose. This is what we also experience otherwise in a way. There were, a few other things we would like to share with you. We are rejuvenating our journal of physics education, which we were publishing, which has been published since 80s. And we are actually starting a series in that in the form of some reviews. That, for example, if somebody can come write a review and we would like to publish. And I think PER is one such area in which we feel that people need to come forward and write such reviews so that more and more people from schools and colleges and universities may understand the import of this kind of a subject, which is now very, very fascinating area of research. And as you mentioned about Paul Wieman and many other people, I remember I was reading one paper where the title was "What Economics Education People Can Learn from Physics Education." It was a beautiful paper which I read. That is how I and Sapna actually started thinking about it. And Carl Wieman's famous paper that "Are we teaching science scientifically?" That was a very interesting question which was coming. So what we would like is, IAPT is a kind of a voluntary organization. And our effort is, and I think this starting of this series itself is part of that, thought process, that we should really bring these kinds of things which are happening so that we can take those things to the classroom. The way you have developed worksheets, can we really also do those? Because in our country, problem is not just of creating those, but also creating those for people who are speaking different languages in different regions. Those multilingual approach is needed. For example, if I want to give, say, FCI to my students, I know that if I have to go to Odisha, I have to give that in Odia. If I have to go to Punjab, maybe I will have to give that in Punjabi. So all these things are also there, which are in our mind. And we will really welcome you to be, coming, interacting with us. I think we will create windows for that. And also, as Professor Pradhan said, we have an IAPT bulletin, which actually comes every month. And sometimes, you can suggest us also. We can request authors also that we would like to have a one-page article. You were mentioning about those articles. I was thinking about your own, that small article which you have put in your website, that how you made a transition to PER to publish in our IAPT bulletin with your permission itself. So I think we would like to really start those things also, so that it goes into the space and we will start thinking a lot about it. And let me tell you, Professor Chandralekha, that lots of things are happening here. There were very many people in this audience also who are working with the students. There is one program of Anveshika, and I hope you know Professor S.C. Verma from IIT Kanpur itself. He is conducting Anveshika programs under the banner of IAPT and his own Shiksha Sopan. So I think those are very interesting things, but there, the education research methodologies of physics education research are not being applied. So what is the impact of all those things? I think we are not able to really assess and see. IAPT as a body would really like to look at those things also. And there we would like to really shake hand with you. That's precisely what I want to say. And let's hope that we will have more opportunities. And from core of my heart, I thank you very much that you immediately accepted our invitation, as Sapna was telling me, to come and share your knowledge. And I think you have really given very good one-liners also, which we can share with our audience later, that what we really need to do. Like when you said, have belief in yourself, and all such things are possible. Ma'am Pragya Nopani is one who is working a lot on experiments, and she is asking that how can we connect to you? So we will give her your email address. I think we will try to circulate with this audience. We have about 10,000 members in IAPT. It's a huge group of physics teachers and physics community. And we are looking forward to such things more often. Thank you very much from my personal side and from IAPT also.
Well, thank you so much. It would be wonderful to do all of those things that you actually mentioned, because, I really want to actually work with you all to see that, we all do something really great for India. So that'll be really nice. I'm looking forward to that. And thank you so much for having me.
Thank you.
Yeah, thank you so much. Thanks a lot.
Thank you. Sapna, please take over.
Yes, sir. Yes, sir. So thank you very much, ma'am. We have taken your times almost 2 hours. So yes, yeah. So I would like to thank you for interacting with the audience, and I would also like to thank Professor Ahluwalia for making this happen. Actually, Professor Pradhan for coming and joining us. So thank you very much, ma'am. I will be in contact with you, and I will. The material which you are going to share with our all participants. So I will contact you. So once again, I thank you very much from on the behalf of IAPT and from all of us.
Thank you
India.
so much.
Thank you very much.
Thanks a lot.
Thank you.
Thank you. And
have a nice evening.
thank you. Namaskar.
Namaste.